In this example, we are going to be using integrals to find a volume. So here's our situation that we have. We have the region bounded by the y-axis. And so it's cutting off these graphs. And then we're also bounded by this function, which is our quadratic on the top. So 8 minus x squared. Right? So I know the quadratic is going down, and then we have an exponential. That's the purple one. That is going up. So there's our other bound on it. It says it forms the base of a solid, cross sections perpendicular to the x-axis. So cross sections that are perpendicular to the x-axis are semicircles. We want to find the volume of this solid. So what we have going on is that you have this base, and then from the base, you're making these semicircles from here. And so it kind of just continues and gets bigger and bigger. And if you went in this direction, it's getting smaller. And so you're kind of creating this three-dimensional shape. So what we're trying to figure out at some point is for us to find the volume, we need to do the integral of the area times dx. All right, so that's the trick. How do we figure out the area that we're talking about? So the area is going to be of these semicircles. So if we kind of just take a snapshot of one of them, right? So if that becomes this base right here is changing, right? It's small here, but larger here. So to figure out what that length is, it's actually just going to be the difference between these two. It's because this one would find all the way down, and then this would find this height. And so we find the difference between them in order to get the actual length of what's left over. So for that, base is this base right here. And that's going to be 8 minus x squared. So the top equation minus the bottom equation. So that would be the diameter, right? We need the diameter because how do we find an area of these semicircles? It's going to be pi r squared, but that's the area of a whole circle. We're cutting it in half. So that's our area of our, so that's going to become an equation that we're going to be subbing into this, right? So we need the, if we have diameter, we need the radius. The radius is going to be half of this, 8 minus x squared minus e to the x. All right, and so we're going to divide that by 2 to get our radius. That is what we're subbing into this. So our area formula is going to be pi times this, 8 minus x squared minus e to the x divided by 2. And that is our radius squared. Then that whole thing is being divided by 2 because they're semicircles. All right, so that whole thing represents the area of our semicircles, but the radius is constantly changing, creating small semicircles on this side and large semicircles on this side. So it's constantly changing. So I might make one little more thing, kind of adjustment to this, just to make it maybe easier. This is probably going to have to go into the calculator at some point. So let's see if we can do this. I'm not even going to divide that. I'm just going to leave it like this. Okay. Okay. So let's start building our calc part of this. So we'll have our volume is going to be an integral. Now, the tricky part on this is we're bounded by 0 and that x value right there. So I don't know where that is, but that is going to come from us taking the two equations and setting them equal to each other. So we're not going to do that algebraically. We are going to throw it in the calculator. So if I throw this into the calculator, we're going to do 8 minus x squared and then e to the x. And I'm going to graph this. I don't really know what my window looks like. Ooh, window looks good. So there is my two graphs, kind of mimicking this perfectly. And then I want to figure out where they intersect. So I'm going to look at where this graph enter, intersects that graph, enter. We'll get it somewhat close to it. Okay. Now, so there's our decimal. Now, I don't have a clean version of that, so I'm going to use all the decimals to be as accurate as we can, especially if you're plugging it into some program and you cut it off at 6.5 or 6.6, and then you use this integral, it's just going to make it off enough that you're probably going to get dinged. So I'm just going to use all of it. That way I'm not going to get dinged. So I'm going to have a 165, 1.658, 2607. Okay, so there's our integral, there's our bounds. And then our area formula is our area formula. So it is 1/2 pi. Here's our radius, 8 minus x squared minus e to the x divided by 2, radius squared dx. Right, which ends up actually being the thickness of each of these things. So the thickness is infinitely small, and it'll calculate it all out, create our volume. All right, so since that bound was dictated by a calculator, 1.658260707, I'm going to be throwing this into the calculator as well. So calculator. So our volume is going to be, let's make sure we throw this into the calculator correctly. So I'm going to go to F2, so green F2, and down to my integral, and I'm bounded by 1 or 0 to 1.6582607. And then we're going to have 1/2 pi. And I'm going to do the fraction. Nope. That's not what I wanted. So we're going to go 0 to 1.6582607. My button. And then we'll do 0.5 pi times fraction 8 minus x squared minus e to the x over 2. And then square that, because that's the radius squared. The calculator do all the math for us. So that gets us a volume of 15.962. 15.962. All right. And that is finding the volume. The tricky part is coming up with this formula, like recognizing that this is what you got going on. You have these semicircles that are creating it. So I need to technically find the area of the semicircle, which is this equation, and then I'm plugging it in. Some of these problems will be non-calculator. This one happened to be calculator right from the get-go, because the only way I'm going to find where they intersect is throwing that into the calculator.